All right, let's dive into a paradox that's right at the heart of, well, everything digital. How can a machine that's built on pure, predictable logic ever create something that's truly, completely unpredictable? This is all about the quest for true randomness, and it starts with a famous warning from one of the giants of computing.
You really have to begin right here, with this legendary line from the pioneer John von Neumann. What he's saying is, look, computers just follow instructions. They're deterministic. You give them the same input, you get the same output every single time. But for everything from cryptography that protects your bank account to the shuffle button on your music player, we need them to be unpredictable. So what gives? For decades, this quote was basically law. The takeaway was simple. A computer, this machine of pure logic, could never, ever create a truly random number. The best it could do was fake it with something called pseudo-randomness, sequences that look random, but if you know the secret starting number, you can predict the entire thing.
But what if that's not the whole story anymore? I mean, our modern computers are worlds away from the machines von Neumann was working with. And that brings us to this fascinating little experiment that someone posted on Stack Exchange, and it seems to flip all that old wisdom right on its head.
The whole thing starts with this ridiculously simple line of Java code. It's running in a loop, and all it's doing is grabbing the system's clock time down to the nanosecond, and then it just lops off the last little piece of that number, the part that's changing the fastest, and writes it to a file. That's it.
And the results were just wow. When you take that data and turn it into a picture, it looks like pure TV static, a totally unique, chaotic pattern every single time. But here's the real kicker. The file was almost impossible to compress. Now think about that. Compression works by finding patterns. This data had no patterns to find, which is a huge clue that it's packed with randomness, or what scientists call high entropy.
And this wasn't just a gut feeling. When this data got run through the official NIST tests, the gold standard for this stuff, it scored an incredible 5.6 bits of entropy per byte. Now, a perfect random sequence is 8, so 5.6 is shockingly high for something that came from one simple line of code.
So this leads us right to the big question, doesn't it? All the evidence seems to scream that yes, we did it. Did the crazy complexity of modern PCs finally let us break the rules of determinism? Did we finally figure out how to commit von Neumann's sin and get away with it?
Well, to unravel this, we have to look really closely at what von Neumann actually said. Because the answer isn't about the program's logic. It's all about the chaotic, messy physical world that the program is running in. And here is the absolute key. Von Neumann warned against using deterministic means. And that little Java experiment, it wasn't purely deterministic. That call to system.nanotime is a non-deterministic operation. The number it gives back doesn't just depend on the code, it depends on the exact physical state of the entire computer at that precise nanosecond.
You see, that one line of code is acting like a tiny antenna, picking up chaos from the real world. That nanosecond reading is being influenced by tiny jitters in the CPU's clock, by the operating system juggling hundreds of tasks, by a packet of data arriving over your Wi-Fi, even by you just moving your mouse. The code isn't creating randomness out of thin air, it's harvesting it from all the noise of its environment.
Okay, so if the big secret is to harvest physical chaos, how do we do it right? That Java code was kind of an accidental harvester. Modern systems have learned this lesson, and now they do this stuff on purpose, building chaos collectors right into the hardware itself.
The perfect example of this is Intel's RDR-End instruction. This isn't software at all. It's a special little circuit built right into the CPU. Its whole job is to measure physical phenomena like thermal noise, literally the random jiggling of electrons inside the chip because of heat, and use that chaos to spit out truly random numbers whenever a program asks for one.
But if you want the ultimate, purest source of randomness, you have to go quantum. The idea is you take a quantum bit, a qubit, and put it into this bizarre state called a superposition, where it's both a 0 and a 1 at the exact same time. Then you measure it. The act of measuring forces it to pick one, either 0 or 1. And according to the fundamental laws of physics, that choice is perfectly, completely, fundamentally random. There's no hidden reason for the outcome. It's pure chance. So there we have it. We've got hardware that listens to the fizz of electrons and quantum machines that tap into the fabric of reality. Problem solved, right? We're all good? Well, not so fast, because generating randomness is one thing, but actually trusting it is a whole other can of worms.
And this is where a healthy dose of paranoia kicks in, summed up perfectly by the Linux developer Theodore Tso. That RDRN chip from Intel, it's a black box. We can't look inside. We can't audit the design. So how can we be 100% positive that there isn't some secret backdoor built into it?
And look, this isn't just tinfoil hat stuff. In 2020, researchers found a flaw they called crosstalk. It literally allowed a malicious app running on one part of the CPU to spy on and steal the random numbers being generated by RDRAND for a totally separate secure program. They even used it to steal an entire encryption key. So yeah, the black box can leak. Even our perfect quantum source isn't so perfect right out of the box. This chart shows the raw data from an actual IBM quantum computer. You'd expect a perfect 50-50 split, right? A perfect coin toss. But it's not. Because of tiny imperfections and environmental noise, it was slightly biased, spitting out a few more zeros than ones.
So what do you do with a loaded die? Well, you use clever math to clean it up. You apply post-processing algorithms to whiten the data and remove that bias. And the hilarious irony here is that one of the classic techniques for doing this was first proposed by, you guessed it, John von Neumann himself. Even the purest randomness needs to be laundered before it's ready for cryptographic use.
Okay, so after this whole journey, from a simple line of code to quantum physics and leaky hardware, let's circle all the way back to the beginning. Was von Neumann wrong? Let's deliver the final verdict.
And the verdict is, von Neumann was completely 100% right. He was never wrong. His warning was incredibly precise. He didn't say computers can't produce random numbers. He said they can't do it by deterministic means, by pure logic alone, and that is just as true today as it was in the 1950s. The only reason that Java code worked, and the whole reason things like RDRN even exist, is because we've completely embraced his point. We didn't defy his rule. We engineered our logical machines to have little windows that open up to the messy, non-deterministic physical world so they can siphon off the chaos they need. Our entire security infrastructure is built around his warning, not in spite of it. And that leaves us with this one last kind of wild thought to chew on. The security of everything we do online, our money, our messages, all of it, is built on a foundation of carefully harvested physical chaos. We trust our digital world because we trust that at its very core, it's tied to a physical world that is and always will be fundamentally unpredictable.